I will start my presentation of improved performance of CEA MFC with increased reactor size. Table of contents. The first is introduction, the second is experimental, the third is results. The fourth is discussion. Introduction. Wastewater treatment accounts for about 3% of electrical energy consumed in the U.S. and other developed countries. MFC provides a completely new approach for energy generation. However, great challenges in further increasing power density have had a plateauing effect on attainable power outputs of MFCs, so maintaining performance during scale-up has proven to be challenging. Air cathode MFCs hold a greater promise for practical applications. But the volumes of most air cathode MFCs studied have been relatively small. CEAs produced a high power density of 1.55 kilowatts M3, and the liquid volume was only 2.5 milliliters. Therefore, increasing reactor size doesn't necessarily lead to a significant increase in total power output. In this study, the use of a new separator material, U-shaped T-current collectors, an oxygen-tolerant microbial community, and improved operating conditions resulted in further improvements in MFC performance. Experimental. A non-woven fabric layer was sandwiched between the carbon cloth anode and the carbon cloth PT-PTFE cathode to form a CEA. U-shaped T-wires were used as the anode and cathode current collectors in both CEAs. The CEAs were placed in between three identical acrylic frames with 5 20 cm openings to form a 5-layer sandwich structure. 3 1 cm by 1 cm crosses were cut through the anode and cloth layers of CEA1 to release the possible biogas produced between the anode and cathode. For CEAs, 3 holes, 0.3 cm, were punched through the T layers to allow venting of possible biogas. The reactor had a liquid volume of 30 milliliters and a total effective surface area of 200 centimeters 2. Figure 1 shows the photo and assembly schematics for the double CEA MFC. The MFC was inoculated with a mixed bacterial culture from the anode of an air cathode. MFC was inoculated with domestic wastewater from the Corvallis wastewater treatment plant. Acetate 100 m was used as the substrate, and the medium solution contained the following. The MFC experiments were operated at 30:1 C in a temperature-controlled lead chamber. Batch mode was initially employed, and the system was switched to the continuous flow mode after 2 days as the power output started to increase significantly. A portion of the effluent was recirculated back to the influent. A 50 milliliters bottle was included in the recirculation line to collect the possible gas. Voltage V was recorded using a multi-channel data acquisition system and used to calculate the volumetric power density and surface power density. The contact and wiring resistances about 0.06 ohms were considered in the calculation of current I and calculated by measuring both voltages over the resistance box terminals and over the current collector T wire terminals. The internal resistance of each CEA was calculated from the linear parts of the IV polarization curves. Area-specific resistances were also calculated by multiplying the internal resistance by the projected electrode area. Acetate concentrations were analyzed with LC. The gas was immediately injected into a GC with a syringe. C was calculated based on the ratio of the average current and the theoretical current. Results. The startup of the larger CEA MFC was much faster and easier. In Figure 2, in less than 5 days the MFC generated a stable high power density. This power density was much higher than the 1.01 kilowatt M3 and 1.55 kilowatts M3. The startup, with thinner separators, suggests that the anodic biofilm can tolerate high levels of dissolved oxygen. To investigate oxygen tolerance at the anode, oxygen was pumped into the MFC chamber at a speed of 20 milliliters m. The power density decreased after pumping the air into the MFC. Figure 3. The fluctuation was possibly due to the much faster airflow than liquid flow. So, the mixed bacterial culture can tolerate high levels of oxygen in water and even direct contact with air. While the power density of CEA2 was stabilized at 1.600 14 Wm to the power density of CEA1 reached a maximum of 4.30 Wm2 at an HRD of 1.37 H. That was more than double the 1.8 Wm2 produced in the small MFC with similar reactor architecture and buffer strength. Power densities were over for Wm2 with HRD in the range of 0.7 to 2.4 H, but decreased outside this range. Figure 5. The high current densities contributed to the high CE, which was in the range of 74 to 98% at the tested HRDs. Figure 5a. The removal of the recirculation increased the CE from 74% to 80% while slightly decreasing the power density by 4%. The complete removal of recirculation decreased the power density by 21%, although the CE was further improved to 85%. These results demonstrate the importance of recirculation. Oxygen diffusion might be affected by recirculation as well, resulting in a slightly lower CE. Increased HRD resulted in increased acetate consumption. Increased HRD also resulted in higher effluent pH, indicating higher CO2 release at longer HRDs. The absence of recirculation slightly decreased the effluent pH and acetate removal, probably due to the reduction in power density and current density. Buffer concentration plays a major role in facilitating proton transport from anode to cathode in an MFC, greatly affecting the internal resistance and thus the performance of an MFC. The production of CO2 in an MFC may increase the concentration of bicarbonate, another effective proton carrier, thus lowering the internal resistance and enhancing the power density. The power density of the MFC with 50 m phosphate buffer increased 5% to 3.40 Wm2 when the acetate concentration increased from 100 m to 150 m at HRD of 1.2 to 1.28 H. It further increased 9% to 3.70 Wm2 when HRD increased from 1.2 to H to 3.00 H with acetate concentration of 150 m. Such a power density is about 3 times of that produced in the small MFC with 50 m phosphate buffer and 30 m acetate. The power density increased 11% with the increase of buffer concentration from 50 to 100 m. Further increasing the phosphate concentration to 200 m only resulted in a 5% increase to a maximum of 4.32 Wm2. The increase in power density was much smaller compared with the 45% and 11% observed in the small CEA MFC when the buffer concentration was increased from 50 to 100 and 200 m, respectively. Such results suggest the role of self-produced bicarbonate in reducing the internal resistance and enhancing the power generation. Discussion. The maximum power density of a CEA MFC increased from 1.8 to 4.3 Wm2, despite the increase in electrode area. The specific cathode area, 667 meters to M3, of the CEA MFC is also much higher than those, 100 meters to M3 or less, of the liter scale MFCs. The higher power density based on the cathode area and higher cathode specific area of the CEA MFC resulted in 8 to 4 orders of magnitude higher volumetric power density. Although the volume, 30 milliliters, is 2 to 3 orders of magnitude smaller than the liter scale MFCs, it produced a comparable or even a higher total power output of 62.3 meters W. The CE of the CEA MFC in this study is also higher than the liter scale MFCs. The factors that might contribute to the improved performance include the use of thin and high flux separator material and U-shaped titanium wires, the development of oxygen-tolerant anodic biofilm, and the enhanced self-production of bicarbonate buffer. The membrane and electrolyte often contribute most to the internal resistance. For example, the electrolyte contributes 78.2% of the internal resistance. The most effective way to enhance the performance is to reduce the electrolyte resistance, which can be achieved by reducing the anode-cathode spacing and increasing the pH buffer concentration. Reducing electrode spacing can proportionally decrease the area-specific electrolyte resistance and in turn the internal resistance, thus enhancing the performance. That can increase the ratio of the electrode surface area volume and in turn the maximum volumetric power density. A sandwich structure of membrane electrode assembly, ME, can effectively minimize the electrode spacing and enhance MFC performance. The inclusion of a CEM needs to be carefully considered due to its high area-specific resistance. CEMs block the diffusion of proton carriers, resulting in a high cross-membrane, pH, gradient, and resistance. The proton transfer rate is limited by the H2PO for diffusion rate, which can be calculated based on Fick's law. The proton diffusion rate may indeed determine the maximum current density, which can be enhanced by increasing the buffer concentration, or reducing the electrode spacing, or separator thickness. The maximum current density almost doubled to about 20 am2, with a 50% thinner separator material. Reducing oxygen crossover is a major function of separators in MFCs. The elimination of the membrane and separator-free single-chamber air cathode MFCs increases the power density due to a decrease in internal resistance. However, the separator-free system results in lower CE. The anode-cathode spacing was reduced to less than 1 mm, significantly enhancing the power density while improving the CE at the same time. The thickness of the separator can be further reduced with the development of an oxygen-tolerant anodic biofilm. A side effect of a thinner separator and reduced electrode spacing is increased oxygen crossover, which may lead to the growth of oxygen-consuming heterotrophs. The higher oxygen crossover may lead to decreased CEs. However, the high CEs, 83.5–10.6%, achieved in this study. This might be due to the high current density achieved in the CEA MFC. The relatively lower actual CEs, 83.5–10.6%, indicated that the substrate consumption in the recirculation line and for biomass synthesis should also be considered. The high CEs are possible even with a low mass transfer resistance separator, as thin as 0.3 mm. The oxygen crossover should not be a major consideration in the selection of separator materials if the anodic biofilm is oxygen tolerant and the current density is greater than 15 am2. Thank you.